So we're going to be talking today, this is topic 4.3 for calculus, and we're going to be talking about balloons initially. So birthday balloons, Gina is throwing a surprise party for her best friend and wants to decorate with helium balloons. As she watches the store clerk fill the balloon, she starts to wonder how fast is the balloon growing. Helium is being pumped into a spherical balloon. What equation relates the radius of the balloon to the quantity of air in the balloon? So since it's a sphere, this is the formula for volume of a sphere. 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 I don't know how to spell sphere. There we go. That's right. Volume of a sphere is equal to V equals 4/3 pi r cubed. Now if you're thinking, well, I'm never going to remember that. How am I supposed to know? Most of the time on an AP test, they will give you formulas like these. They don't expect you to remember them, except for like area of a triangle or area of a rectangle. And unfortunately, area of a trapezoid will not be given to you. So those are the ones you have to know. We'll talk about those more when we need them. But really, volume of a sphere, they're going to tell you what that is. Volume of a rectangular prism, not so much. So let's go ahead and get started. A couple of colors out. So find the time find the radius of the balloon at each volume. So they're giving us the volume. I'm going to take this formula and manipulate it so radius is alone. First thing I'm going to do is times by 3/4. So 3/4V equals pi r squared, because just flipping that over, dividing by a fraction means multiply by the reciprocal. And then I'll move pi over. It'll be down here with 4. And we'll take the square root as we go. So we're just going to plug in 2 into this and see what's going on. So this way I can use my calculator for the most part to do this for me. It's not going to be perfect, but it'll do. So when the volume is 2, that means we get 6/4. I want my calculator to do this for me. That's what I said. So we only need the positive square root, so let's go ahead and finish this. R is equal to the square root of that. Okay, so I'm going to use my calculator. Turn it on, go into y equals. I'm going to change this for that formula I just created. So it'll be the square root, the square root of a fraction 3/4 pi times our variable. And so even though we've got this all mixed up this way, we'll use the table. So then we're going to set up table setup. We're going to do independent. We're going to do ask. Okay. And so let's go look at our table. And so we're going to plug in 2 feet. And we get 0.691. We'll plug in 4 feet. 0.9772. And then 6 feet. 1. Wow, that looks really good. That's funny. But it wasn't blurring, so we'll use it. 1.1968. 8 feet cubed. 1.382. And 10. And I get 1.5451. Okay, and so there we go. And so you'll see what I did is I solved this equation for R. I didn't show my work, so let me go ahead and write that down. So I solved this given equation for R. So what I did is I divided by 4/3 on both sides. And that gave me 3/4. v equals pi r squared. Then I divided by pi, and it went down with 4/3, the 4. So I had 3/4 pi v. And then I took the square root. And I only needed to worry about the principal square root because it had to be positive because we're talking about a radius of physical objects. So I didn't use plus or minus. So, in case you're curious. And then I used my calculator, plug that into my calculator. My calculator gave me all those numbers. All right, at what rate is the volume changing? So when I look at just the volume, so I've got my time is 1 second, volume is 2, time is 2, volume is 4, 3, 6, 2, 4, 8, I have 10. At what rate is the volume changing? Go back. Looks like 2 cubic feet per second. So time's measured in seconds, volume is measured in cubic feet, radius is measured in feet. So I should really have put feet after every single one of these. So anyway, okay, is the radius changing at a constant rate, and how do you know? So the volume is changing at a constant rate. Is the radius changing at a constant rate, and how do we know? So I'm just going to look at the change between here and here. So in other words, I'm going to subtract, right? And so we'll go ahead and quit out of here. And I need to do 0.9972. Wait, excuse me, 2 7s, not 2 9s. Again, another reason I like this calculator, minus 0.0691. Whoops. And so my answer is almost 0.3. And so then let's do this, the next one, 1.1968 minus 0.9772. And you'll notice those are not the same. So I'm going to say no, because those two numbers aren't the same. If it was changing at a constant rate, as I subtracted them, those would be the same. Because think about that. If I go back here and I subtract, I get 2 every time. So, no, because r at 2 minus r at 1, the radius at 2 seconds minus the radius at 1 second, which would be 0.9772 minus 0.691, which is equal to 0.2862. Okay, so that's that part. And the radius at 3 minus the radius at 2, which is 1.1968 minus 0.9972. Wait, why I think that's 2 9s. I'll look at my table. Maybe I wrote it down wrong and my brain's trying to correct it for me. Nope, I wrote it down right. Okay. And so that was equal to 0.2196, and they are not equal to each other. So they're not equal, therefore the rate of change is not constant because they would have to be equal. So in other words, the rate of change is changing. All right, so the volume of the balloon depends on how much time has passed, right? The volume depends on how much time has passed. And so we can rewrite our volume as a function of time like so. Okay, what is the independent variable? Whenever time is involved, itself. Independent variable is time. Okay, let's go ahead and find the derivative. Okay, so notice we're taking the derivative with respect to time. It's very, very, very important. So the derivative of the volume with respect to time is dv dt equals 4/3 pi, which is our constant. Let's go ahead and move this up. which is our constant, times our R3 comes down, R of t to the second power times the derivative of the inside, dr dt. Okay, let's clean that up just a little bit, just a little bit of cleaning. 4/3 pi times 3 is just 4 pi. R of t to the second power, dr dt. So that's where we are. Okay, just a little cleaning, not much, just a little. At the instant when the radius is 1.5 feet, how fast is the radius changing? So what we're saying in that question, when r of t is 1.5 feet, how fast is the radius changing? They're giving me this number. We're going to use our answer from question 3 to help us. How? Well, we said this is the rate at which the volume is changing, right? And it's cubic feet per second. So this is actually dV dt. We didn't write that down, but it is. dV dt is 2 cubic feet per second, which is huge because now I can plug something in there. I'll be able to plug in here, and all that will be missing is this unknown. So I'll be able to replace dV dt, R of t, and I will not replace this. So here we go. We've got dV dt. Let's just write it one more time. We're going to dV dt is going to get replaced. Put a next box around that, equals 4 pi, and R of t is going to get replaced. And we not replace dr dt. Okay, so we've got dV dt is 2 feet. This leads to dV dt is 2 feet. Cubic feet per second. We'll come back to that for units in just a minute. And that's equal to 4 pi times 1.5 feet squared times dr dt, which we don't know. So you'll notice this went in and this went in, along with the units. So 1.5 squared is 2.25, because 15 squared is 225, so 1.5 squared is 2.25 feet squared times 4 pi. Okay. 4 times 2.5. 2.25 is 9. So we get 9 pi feet squared dr dt. So we have 9 pi feet squared dr dt equals 2 feet cubed per second. Now we're going to divide. I'm carrying the units around on purpose. So I want you to kind of understand that the units are there on purpose. I'm going to write them wrong. So I'm just going to steal some paper, stick it right here, and keep writing. Okay. And so there we go. Okay. So I'm just going to divide. I've got 2 feet cubed per second divided by 9 pi feet squared equals dr dt. I am officially finished. I'm just going to clean up the units. So I have 2 over 9 pi. And feet cubed divided by feet squared is feet per second equals the rate of change of the radius. That's wrong. Where's t? Where's R? I got a constant. It's not a constant. Wasn't changing a constant rate. What's wrong? Oh, when? At the instant. I didn't read the question. Let me go back and read the question, then I'm fine. At the instant when the radius is, how fast is the radius changing? Okay, so this is not always drdt is. drdt at r equals 1.5 feet. Okay, I feel better about that. Okay, so it's really important that we know that. That's a specific number. And I can make this a decimal. I'm not going to. I like it like that. I'm a big fan of accurate answers. Okay. Now, last question on this page. Getting back to it. Is the radius going faster when the radius is small or when the radius is large? So the rate of change of the radius, which is dv/dt, which is a constant. So that part's still true. So this 2 is always true. Okay. When the radius is big or small, when is it changing faster? So I'm just going to kind of actually, to do that, I'm going to go back here. I've got 2, and I'm just going to ignore units for just a minute. But the units of the radius will be feet per second. So we know that now. So I'm going to write 2. Equals 4 pi r of t squared dr dt. And so I really have 2 divided by 4 pi and r of t squared, like that. I'm just dividing all of that over. So thinking about the fact that r is in the denominator kind of changes things, by the way, what's going to happen here. And so we go back here, and we also can tell by our table. So let's actually take a look at our table. So what do you think? We have this smaller. When the radius was small, it was changing at this speed and this speed divided by 1 second. Okay, so the 1 second is the divider every time. So per second it's changing. And so I think it's changing when it's small. And because of looking at this table, just so you know, I wrote down small down there. By looking at this table, I can see the numbers are getting closer together. Like these are only less than 0.2 apart. These are more than 0.2 apart. Maybe, just barely. Those are just a little over 0.2 apart, and these are almost 0.3 apart. So, yeah, it's changing faster when it is smaller. Growing faster when the radius is smaller, and that is because we're dividing by the radius. And so when you divide by a larger number, you get a smaller number. There you go. Okay. Are there any questions about that? Well, we'll see. So last we have our lovely table to write down for this video. And so let's jump over to the pretty already written out version of what we're talking about. So for related rate problems, the first thing you do is draw a picture. Now we didn't draw a picture with our sphere because it's really hard to draw a sphere. I should have. We're going to write an equation that relates all the variables in the problem. So it's usually a volume formula or it involves the Pythagorean theorem. We're going to take a derivative of both sides with respect to time most of the time. Don't forget to chain rule on your normally independent variables. Like when you think about, see, this is why I like the other, I'll get it back. When we think about things like v equals 4/3 pi r cubed. When we think about that, r is the independent variable in this situation most of the time. But now our independent variable in our problem was time. And so we had to chain rule r when we were taking its derivative. And it's really easy to forget. Plug in the known values and solve for the quantity you're after. Based on the context, determine if it's positive or negative. Because sometimes the sign of it won't actually match. So make sure. Now ours is growing, so it's positive. So that's important. Okay. We'll talk to you soon. Have a great day.